Imagine a completely empty plot of land. Now picture an enormous, high-tech factory springing up right on top of it. In the engineering world, we call this a greenfield project, building a massive industrial operation entirely from scratch, exactly where nothing existed before. When you build from the ground up, you are pouring billions of dollars into a single location. To protect that massive investment, you have to design systems that can anticipate every electrical surge before the first concrete foundation is even poured. This flowchart maps out that strategy. If you follow the path from the initial greenfield blueprint node straight over to the critical risks and safety infrastructure box, you can see how identifying dangers early is built directly into the original design. And the biggest external danger that factory will face comes from the sky. A single lightning strike carries over 100 million volts of electricity and can heat the surrounding air to 30,000 degrees Celsius. That is 5 times hotter than the surface of the sun. If that kind of power hits an unprotected building, the results are immediate. It causes sudden fires, severe structural damage to concrete and steel, and instantly melts the delicate computer systems running the operation. To survive, a modern factory has to act as an invisible fortress. Without these defenses, an afternoon thunderstorm can spark fires and destroy the sophisticated electronic systems that the factory needs to function. Let's look at how those defenses actually work when a heavy, violent storm rolls over our newly finished factory. This diagram shows our first line of defense in action. Right at the top, you will see a tall metal spike called an air rod, or lightning rod. Its job is actively invite the lightning bolt to strike it, rather than letting the lightning find a random, vulnerable spot on the roof. Once the rod catches that massive surge of power, it hands it off to a down conductor. Watch how the energy moves. This thick, highly conductive cable acts like an electrical express lane, pulling the current safely down the exterior walls, keeping it far away from anything inside. At the bottom, the conductor connects to an earthing system. Here, the energy hits a subterranean web of metal rods buried deep in the soil. The ground easily absorbs the shock, spreading the voltage out until it harmlessly fades away into the dirt. But sometimes, a tiny ripple of that shockwave tries to sneak its way inside through the power cables. To stop that, engineers install surge protection devices, or SPDs. Think of them as heavy-duty shock absorbers that catch and neutralize those leftover electrical spikes before they can reach the sensitive equipment. The goal of external electrical protection is not to fight the storm head-on. Instead, the design simply provides a highly attractive path of least resistance, guiding the danger safely around the critical machinery. The weather outside is not the only threat. Sometimes the danger starts indoors. A large factory motor might overheat, or its internal wiring could cross, causing a sudden, dangerous surge of electricity known as a short circuit. To manage these internal issues, facilities rely on equipment like this tall, gray industrial electrical switchgear panel. You can think of this cabinet as the factory's electrical nerve center. It constantly monitors and directs the flow of power to every single machine on the floor. Housed inside that switchgear are individual circuit breakers. As you can see on this detailed control interface, these are highly complex devices. They act like rapid response blast doors, constantly scanning the electrical current. If they detect too much power flowing through, which engineers call an overcurrent, or if electricity starts leaking into a machine's frame, the breaker snaps shut to stop the flow instantly. But there is a catch. If one small motor fails on an assembly line, you absolutely cannot afford to let that one single breaker shut down power to the entire multi-billion-dollar facility. To solve this, engineers use a coordination technique called sequential trip settings. This is a way of organizing the breakers so they communicate with each other and agree on exactly who should act when a surge happens. This tree diagram illustrates how that intelligence works. When a fault occurs at a machine down at the very bottom, only its immediate parent connection breaks. The rest of the tree stays fully powered up and running perfectly. By isolating the problem to a single machine, this smart routing prevents a massive, costly factory-wide blackout. What could have been a catastrophic shutdown becomes a quick, routine maintenance repair. Between the external rods steering massive lightning strikes into the dirt and the internal breakers isolating local mechanical failures, the factory operates inside a perfectly balanced, dual-layered shield. These systems are the physical insurance policy for the billions of dollars spent building the plant. They ensure that the facility remains an asset that earns money instead of a liability that costs it. Looking back at our strategy flowchart, we see the final goal: life cycle value realization. This is essentially about making sure the factory stays productive and profitable for decades, rather than being derailed by preventable accidents. A thorough engineering strategy takes the wild, destructive forces of nature and mechanical wear and turns them into highly predictable, manageable events. Mastering the flow of electricity and building safe pathways for it to travel is what makes large-scale modern industry possible.